the greatest integer function. It looks kind of like the absolute value, but it has these brackets around the variable of x. And what the greatest integer function does is it rounds down a real number to the nearest integer. It rounds down a real number to the nearest integer. So for example, let's start with the positive values because those are the easiest ones in terms of thinking about rounding down. So let's start in our table. And yes, this is not your traditional looking table, and it's on purpose because if we use real numbers, those are the integers, or not real numbers. If we use whole numbers, those are the integers. So for example, 0.4, we round it down to the nearest integer, so that is going to round down to a value of 0. So where x equals 0.4, we have a y value of 0. So if you want to go ahead and plot that on the coordinate plane, so you can kind of see what's going on. All right, even with something like 1.75, 1.75 would normally round up, but the greatest integer says you always round it down to the nearest integer, so 1.75 is going to correspond to a y value of 1. 3.333 would round down to a value of 3, so 1, 2, 3 and a third has a y value of 3. 5.99999, that's going to round down to 5. So almost at 6, 2, 4, 6. That's going to round down to a y value of 5. Now, with our negative numbers, we're rounding down. So something like negative 0.9 is actually going to go down to negative 1. Okay, negative 0.9 is going to round down to a y value of negative 1. So don't think about it. Positive 0.9 goes down to 0. Negative 0.9 goes down to negative 1. So negative 2.1, that is actually going to round down to negative 3. 2.1 negative 3. Negative 4.25 would round down to negative 5. And negative 6.5 would round down to negative 7. Okay, so right now we have a bunch of random points. If you still kind of don't see what's going on, let me add just a little bit more detail so you can see. Let me add to our table here. How about, what if we had 1.25, the next value of 1.25? 1.25 would also round down to positive 1. So x value of 1.25, y value of 1. So you can kind of see those 2 points are going to be beside each other. So what this function is going to end up looking like is we're going to have just these segments that are going to have points on the left side, and hopefully, I don't know if I can get enough detail here on mine. The right side is going to be a hole. The left side is going to be a point at every whole number integer here as we step. So like if I plot one where we didn't have one before, we didn't have any y values of 2, but something like 2.5 would round down to 2. So we would get a segment right here. The left side has a point, the right side has a hole. And then that pattern is just going to repeat. This is sometimes also called a step function because it kind of steps up one y value at a time and it remains constant as you go along. So kind of, again, funky looking graph. You don't really run into it too much, but there are some cases in the real world where you do talk about values rounding to whole numbers. Now there are other step functions. Okay, this is not the only one. This is just what we consider the greatest integer function. There's also a least integer function. And then, like with any kind of function, we could like add something inside of here. We could have the greatest integer function of x plus 2. Or you could have the greatest integer of x with a plus 2 outside. So that's going to kind of change the location of the graph. It's going to have the same characteristics, but it's going to be either shifted left or right or up or down or something like that. So not the only one that there is, but this is kind of the most common one that you'll run into. Desmos will do the step function. It's actually called the floor. I think if I type this in right, yep, there we go. Okay, it's called the floor function. You just type in floor of x, and you can see obviously that the same graph is produced. I think I showed you the other day with our piecewise functions. It doesn't show you the points versus open circles, but if you click and drag, you can see that it's true. So -1 is a point over here. If I come over here, it automatically jumps me up to the next piece. So it doesn't really show me the whole. It just jumps me to the next. Well, actually, it does right there, 1, 0. It shows a gray point. That's a whole. Can we get close enough here or not? Yeah, see, like as soon as I touch 2, the point automatically jumps to the next part of the graph. So anyways, just kind of wanted to show you that idea there and let you know what the greatest integer function is. I've also seen it, sometimes you will see it with like a double bracket. It's not just a single bracket. Sometimes you'll see a double bracket, so it's telling you the same thing. Okay, I don't know why the notation there is inconsistent, but I have seen it both ways. Okay, back to kind of the more traditional piecewise functions. You've got a graph there on your paper. We don't have the equations. We don't need the equations. They are asking us to use the graph to evaluate the function for these given values. So let's say, for example, g of -2. The purpose of this exercise is to continue to piece together the fact that when you evaluate a function, that produces a coordinate point. All of your coordinate points together produce the graph. So we should be able to go backwards. If we have the graph, we should be able to pull the point off and be able to pull out the y value by reading the graph. So g of -2, -2 is our x value, so find -2 on your graph. Find where it is on the actual, in this case it is a line, and look for its y value. Its y value is +1. So g of -2 is +1. We could have written the equation of that line, but we didn't need to. Okay, the graph gives us the information that we need. So g of 5, here's our x value of 5. Go down to where the graph exists at that x value, and the y value there is -3. Okay, how about g of 0.5? Again, we tend to think in terms of whole numbers all the time, but there's nothing that says that we have to use whole numbers. 0.5 would be about right here, so we're looking at a point at y equals 1. Similar with something like 4.7. Okay, 4.7, that's close to 5. It's pretty convenient though in this case because it's on a horizontal line, so its y value is of course always -3. Okay, now this is one that tends to mess with people. G of -1. Okay, -1 is of course right here. When we look at -1 though, it looks like we have two values. Okay, it looks like we have two values, but you got to remember this one down here, if that's an open circle, that's a hole. That is not where the graph exists at -1. The graph at -1 exists up here at +1. Okay, g of -1 is +1. It is not -2. Let me add one to this. Let's also look at g of 2. Okay, g of 2, similar situation. G of 2 would be our other changing point for this function. It looks like there are two values, but again, open circle, that means we're not equal. You look for the point, and the point here is also positive. Okay. Any questions about using the graph to evaluate? Okay, example number 10 here. What value of c would make the function continuous? So we've played around with this a little bit with some of the other functions that we have had. But this one, there's a specific part of the function that it's saying, this is what you have to fix. So in this case, we've got to determine what slope on this second function will cause these two graphs to be equal at our changing point. So I'm just going to write down a few notes so that you know what kind of mentality that we're looking for here. In order to be continuous, the two pieces must have the same y value at the changing point. And in this case, it's x equals 2. Not always the case, but for this function, it is x equals 2. So at 2, we have to have the same y value. So to handle this, we're going to plug in the changing point to both pieces. And if they have to have the same y value, then that means they got to be equal to each other. So we're going to plug in the changing point to both pieces and set equal. So let's do this. The changing point is x equals 2. So we plug in 2 for our x in the first piece. That would give us 2 plus 1. We plug in x in our second piece. So we've got c times 2 minus 1. So notice this is just a basic linear equation. We've got one variable. Our variable is c. We should be able to solve this. So 2 plus 1 is 3. I don't know about you, but I don't like c times 2. I would rather write that as 2 times c. So 3 is equal to 2c minus 1. We're solving for our c. So 3 plus 1 is 4. 4 is equal to 2c. So if we divide, 2 is equal to our c value. Check it real quick. When x is 2 and c is 2, 2 times 2 minus 1 is 3. That was what our top piece is equal to when x is 2. 2 plus 1 is 3. So both of them equal the same y value. They both equal 3 at the changing point of 2. Makes sense? Any questions about that? I think I added this after I printed out the notes, so jot this one down really quick. This is the other scenario that they could ask you about with making a piecewise function continuous. So the first one was the piecewise we're used to, left side, right side. They got to meet up at the same y value. We talked about this some yesterday, the equal to and the not equal to. So remember, visualize what these functions are looking like when it's the equal to and the not equal to. Okay, it looks like this function right here, except at this single point. So at this single point, we need the value to be the value that the first part should be. Okay, where it should be, it usually has a hole for one reason or another. So notice, if we just plug in -4 into this function, we just plug in -4. -4 plus 4 is 0. -4 squared minus 16 is 0. 0 over 0 It's not allowed. Think back to Math 3 a little bit. What did we do with these types of functions? We always wanted to simplify in some way or another. The numerator doesn't simplify. The denominator is factorable. It's the difference of perfect squares. We can factor it into x plus 4 times x minus 4. When we do that, now we have a common factor that we can cancel. So our function simplifies to 1 over x minus 4. Guess what? That got rid of the problem. If x is -4, -4 minus 4 is no longer 0. -4 minus 4 is -8. So it's okay now. We can plug in that number and that's what the y value would be if we didn't have a hole right there. So that's the y value that we need. That's the k down here that we need in order to make this continuous. That's going to plug that hole and make that a continuous, in this case, rational function curve. Okay. So our k value is -1/8. So just when you have a rational function like this, you want to factor and cancel. And then plug in the changing point, or plug in, yeah, we'll keep calling it the changing point, even though this function technically doesn't change there, but that's the point of discontinuity. So you factor and cancel these, and then you plug in the changing point, and you've got it. Now, ideally, this is how I want you to handle these problems, because if you go to calculus, there are a lot of problems like this, trying to make functions continuous, so they want you to understand what's actually going on. But let me show you something in Desmos that you will have access to, that you can use during the actual exam if you need to. So I showed you the other day how to plug in your piecewise functions into Desmos. And let me just make sure I've got everything. Yeah, nope, that's supposed to be, that is greater than 2. Okay, less than that. Greater than 2, okay. And guess what you can do? You can type in that c into that function, cx minus 1, when x is less than or equal to 2. And notice down here it says add slider c. You want to do that because what it'll do is it'll start at a default of 1. So you can see these two functions, obviously not continuous. They're not meeting up at the correct y value. You can click this point right here and you can drag it and look, you can watch the function change as we're changing that slope, and you can work it so that it does meet up at that point. You can make sure that they do have the same y value right there. And then it tells you that the c value is 2. So that confirms what we did algebraically. Now, not quite as easy with this one because Desmos does not do the not equal to and the equal to, but let's see here, is that plus 4 over, if you do need to graph a piecewise function like that, the equal to and the not equal to, you do need to understand that it just behaves like the not equal to piece. So I'm just going to worry about graphing that part. So there's what our graph looks like here. Now, it doesn't show us right off the bat, like there's not a big huge gaping circle here at -4 for an open point, but if I do click and drag till I get to an x value of -4, it does tell me that's undefined, and it shows me that point right there. Now, pretty much your goal here is to look at your y values as you get really, really close. So there we're at -0.12, And over here on this side, we're at about negative 0.12. That looks to be negative 0.125. So that's pretty close to it right there. Now, your entire NCFE is multiple choice. So you would have answer choices, and you want to look and see, okay, negative 1/8 is negative 1.25. That's probably the close. I mean, if you don't know how to handle it, if you forget how to handle it algebraically, which works every time, but if you forget that, use your graph. Okay, you know that the point is I'm trying to fix that hole right there. I need my y value to fit right in line with these y values right here. Use the technology to your advantage and compare your answer choices to what you're observing.